Okay, well, let's go ahead and get rolling for today. So I have no pressing announcements for today. So remember, I had delayed quiz 11 until Friday. So, and I would wait a little bit on that. We still have some material to cover before you really be prepared for all the questions on that. Okay. So the exam is now graded. And all we have to do is really just release those grades. One of my TAs put the grades in this morning. So actually, he just got done. So I just need to go back to my office and release those to you. Just look over them and release them. So hopefully this afternoon, there'll be grades on exam 3. I did look at the average. The average was a 73% again. So somewhere around there. So I think pretty decent considering the difficulty of the exam. Okay. So I'll get those out to you, and then we'll of course put those exams in MRB 111 for you to pick up and look at. Okay. I have yet to produce a key, so I'll have to do that. That's not going to happen today. The other thing also is that I also am going to have to cancel my office hours. I made an announcement on the Canvas about this, but I've got some family commitments that I have to attend to this afternoon. So run back to my office, release the exam scores hopefully, and then off to my family commitments, okay? All right, so our riddle here, 4 jolly men sat down to play and played all night till break of day. They played for cash and not for fun, with a separate score for everyone. When it came time to square accounts, they had all made quite fair amounts. Not one had lost, and all have gained. How can you explain? Or tell me now, this can you explain? Very rhythmic, this one, right? What do you think? What's that? Socialism. No. No. That was not socialism. They all played here. Let me give you a hint. A separate score. They had a separate score that they each played. You're a band. This is a string quartet. Yeah, see? All right. Okay. On to material, I suppose. That was fun. As much fun as that was, we have to talk about now the movement of lipids through our bodies. So we... on Friday, left off right here. We had covered on Friday the entirety of what would be considered the exogenous pathway of lipid transport. Exogenous pathway, just as a reminder, a review to you, begins essentially in the epithelial cell of the small intestine, in where we see the development or the production of these chylomicrons. Those chylomicrons are fairly large in terms of what we call lipoprotein particles. I actually have a slide on here, but we'll look at the size of them, okay? But later on. But so the chylomicrons will be excreted into the bloodstream via the lymphatic system. They have these proteins on them, in particular C2, very important protein on the chylomicron, because it will be bound by an enzyme that is anchored to essentially the cells surrounding the lumen of blood vessels, in particular at capillary beds. And that enzyme is called lipoprotein lipase. It will bind to and recognize C2. It will start to then degrade triglycerides into free fatty acids and glycerol. The free fatty acids will then be absorbed by the surrounding tissues. So a tissue that expresses more of that lipoprotein lipase will get a larger load of fatty acids than those that don't have that in the capillary bed surrounding those tissues. Okay, and then the glycerol, because it is soluble, generally speaking, will be absorbed primarily by the liver and even the kidney. And that glycerol will be converted to dihydroxyacetone phosphate by the enzyme glycerol kinase, which is only found in those two tissues. And then that will then lead to this production of a chylomicron remnant. That remnant is essentially a chylomicron that's been depleted of triacylglycerides, as well as C2. Interestingly, the apolipoprotein C2 has more than likely been removed from that remnant, and apolipoprotein E has been put on it. These lipoprotein particles can exchange material between one another in the bloodstream, including some of the proteins. Not all of the proteins, but some of the proteins. And so C2s come off, E's come on, and E then targets these remnants to the liver cell in which they will be endocytosed. And upon endocytosis, they'll fuse with the lysosome. The protein components will be converted to amino acids. Triglycerides will be converted to free fatty acids and glycerol. And cholesterol esters, any that are there, are going to be converted to cholesterol and free fatty acids. Okay? And that would end then the exogenous pathway at that point. Okay? So what we are going to do then today is we're going to pick up right where we left off there and start talking about what would be considered the endogenous pathway. Okay, so let's go to a new slide. The endogenous pathway, okay, or what's called endogenous transport. Okay, and the endogenous transport, this is going to begin or start at VLDLs, very low density lipoproteins in the liver. Okay, we'll talk a little bit about, not too much, and not in a ton of detail, but we'll talk a little bit about the production of VLDLs. And then, interestingly, it's going to end at LDL in the liver. Okay, and LDL is low density lipoprotein. A very low density lipoprotein to low density lipoprotein. Okay, so it starts and ends essentially at the liver. Now, there's a lot between those 2 points, and many of the VLDLs that are put out into the bloodstream by the liver will never actually make it back to the liver. Some of them will be absorbed by other tissues, but many of them will. Okay, so while we say it starts and ends at the liver, there are going to be some that's not necessarily true for. Okay, now VLDLs, let's first of all talk about reasons for their production, and then that will give us a hint in terms of the purpose of what would be considered the endogenous pathway. So there are 2 reasons for the production of VLDLs. The first one, okay, would be to transport excess dietary lipid. Okay? And new lipids. Okay? And all of this, and the reason number 1 would be in what would be called the fed state. Okay, so after a meal, depending on the contents of that meal, there may be excess dietary lipids that make it from the exogenous pathway into the liver. Okay, those free fatty acids that we talked about that may have been endocytosed in the chylomicron. Okay. At the same time, because the body is in the fed state, insulin levels are more than likely elevated. And an insulin elevation in the bloodstream, that will signal the liver to actually make new fatty acids, okay, specifically from excess carbohydrates. Okay, so excess carbohydrates will be converted to new lipids. Those will also be packaged in these VLDLs and sent out to the rest of the blood, or sent out to the blood supply and the rest of the tissues. Okay. The other possible, and this would be less common, but this is also a reason that VLDLs will be produced, and that's to transport free fatty acids. Really, I'll put triacylglycerides, okay? That's the form that they're transported in, okay? Derived from adipose tissue. And this would be more of a fasted state. Okay. In the fasted state, of course, signals would be the opposite in the bloodstream. Signals in a fasted state would be glucagon that would indicate that levels of energy are potentially low because blood glucose is potentially low. Glucagon binds to the liver cell, but it also binds to adipose tissue. We talked a little bit about that. I just mentioned it briefly. But in that, it will actually, glucagon will be a signal for adipose tissue to start to break down triglycerides. Those fatty acids that are being broken down from, or that are being that are derived from the triglycerides in adipose tissue will be transported into the bloodstream on a protein called albumin. That albumin can be taken up by the liver, and then the liver can package that in VLDLs. Okay, so this would be another way to then get lipids to the tissues. In that case, though, the fasted state, of course, the energy need is great, whereas in the fed state, the energy need is not necessarily great. We're thinking more of a storage aspect of things. Okay, so those are the two primary reasons that VLDLs would be packaged and made in the liver. Okay. And that then brings us to our purpose of the endogenous transport. Endogenous transport is essentially, the purpose of it is to, of course, transport lipids from the liver to the rest of the tissues. Okay? And that's really all we need to say for that. Okay? Now, VLDLs, let's go ahead and talk a little bit about what these are going to be made of. Honestly, they're very similar to chylomicrons. Okay, they're made in the liver cell, though, so there is some differences, but they are a lot of similarities. Okay, so when we think about this, so when you go back to the end of the exogenous pathway, we've got these free fatty acids that are arriving in the liver. Or you could think about them even, these are free fatty acids derived from adipose tissues. These are going to have to be converted, and it's about 1 or 2 steps that this happens in. These will have to be converted to what would be considered acyl-CoAs. Okay, I purposely haven't looked at the enzyme that will do that. Okay, and because we'll talk about that later on. We'll get to some of the biochemistry in the inside of these cells, what those enzymes are, what they are doing. But acyl-CoAs have to be made first. From acyl-CoAs, okay, that are being made, those acyl-CoAs can be packaged into triglycerides. Okay? You have to have glycerol, of course, to do that. And then also these acyl-CoAs, another fate of them will be to combine with cholesterol. Okay, if you go back several slides and you look at Friday's notes, you will find almost an identical thing listed there. Okay, in terms of the packaging and production of a chylomicron, same process. Similar enzyme, if not the same enzymes. In fact, this process, again, just to remind you here, okay, that process is catalyzed by this enzyme ACAT, okay, acyl-CoA cholesterol acyltransferase, ACAT. Okay. And that makes these cholesterol esters. Now, when we look at VLDLs, we want to look at the composition of these. Big thing here, so we got VLDLs here. They're, again, very low density lipoproteins. The big thing here would be then that they'd have quite a bit of triacylglycerides or triglycerides in them. About 50% of their weight will be triglycerides. Okay. They are lower in triglyceride contents than chylomicrons, but certainly higher in triglyceride contents compared to the next 2 lipoprotein particles that we're going to look at today and probably Wednesday. Okay? All right. Those will then be exocytosis. I'm going to go exocytosis into the bloodstream from the liver. Okay, the VLDLs. Much of what we're talking about occurs in the ER and the Golgi. Okay, so all the production, even in the small intestine, of chylomicrons or VLDLs here is going to be occurring in the ER and then the Golgi. Okay, and then it will be released as through exocytosis. Okay. Right. Questions on that? No? Okay, awesome. So that then starts the endogenous transport or endogenous pathway. The endogenous pathway looks very, very similar to the exogenous pathway. And I'm going to show you what I mean by that. So what you're looking at here in terms of the endogenous pathway, let me go ahead and highlight what we're essentially mentioning. Okay. The VLDLs come out of that liver cell and enter into, of course, the bloodstream, and then they are transported through the bloodstream. Okay, those VLDLs are going to interact with different enzymes found in the capillary bed. Now, something I failed to mention here, so I need to come back because I just realized I didn't talk anything about the protein composition here. We take these guys, triacylglycerides, we're going to add to these again phospholipids. Okay, I forgot to mention this. Sorry about that. But we'll also add to these apoprotein B100. Okay. We'll add to these ApoC2. And then we'll add to these ApoE and others. All right, so these are the proteins that are found in these. C2 is the same thing that we found in the chylomicron. ApoE, again, the chylomicron picks up ApoE later on. This is made with ApoE, okay, in the liver. And then ApoB100 is similar to B48, okay. So B48 kind of wraps around the chylomicron. Okay, it's this long alpha helical protein. B100 does the same thing, it's just bigger. Okay, and so in fact, the B48 and B100 come from the exact same gene in different cell types. Okay, they come from the same gene, but in the small intestine, they undergo what would be considered alternative splicing. Okay, and several of the exons get removed that make ApoB48 that remain to make ApoB100 in the liver. Okay, so the same gene, just alternatively spliced. Okay. So these three are the major components that you would find in the LDLs. The B100 and the C2 are really important for our discussion. Okay, so these two I want to highlight. And this is why then I was reminded that I need to do that, because on my next slide, okay, we get to this point here. Okay, coming back to here, we've got the VLDL that is exocytosed. It gets to these capillary beds, and C2 starts to interact with, again, that same lipoprotein lipase that the chylomicron interacted with. Okay, so the lipoprotein lipase then is going to take the VLDLs, bind to C2, so I'll put lipoprotein lipase here. Oops. Okay. That will actually remove free fatty acids and glycerol. Okay, these will be absorbed by the tissues, surrounding tissues. Glycerol, again, more than likely is going to make its way back to the liver, the kidney, and I didn't really mention this, but I'll mention it here. Adipose tissue will also take this up. Now, as those triglycerides are removed, okay, free fatty acids and glycerol come from the triglycerides. Lipoprotein lipase is what's doing this. Okay, as those are removed, you get what would be called an IDL. Okay, intermediate density or intermediate density lipoprotein. Okay, so you got VLDL, very low density lipoprotein, IDL, intermediate density lipoprotein, and then finally, same thing remaining in circulation. The IDL will be, again, by the lipoprotein lipase, have free fatty acids and glycerol removed. Until finally you get LDLs, low density lipoproteins. So the whole process is simply, again, package fatty acids as triglycerides in a VLDL, in a liver cell, ship those out, lipoprotein lipase binds to C2, starts to break down triacylglycerides, removes the free fatty acids from those. Those free fatty acids are again absorbed by the tissues, and the glycerol can be transported to liver, kidney, or adipose tissue to make more triacylglycerides, or sugar if need be. Okay. There's obviously other things that are going on to a certain extent, but that's essentially what we see here, okay? Questions on that? No? Okay, well, let's do this. Let's look at a little bit of what's happening here, okay? And someone asked me on Friday the size of these things, and I said, oh, I don't know. I'm forgetting that I had this slide in mind. So I did know, I just had forgotten, okay? But anyway, so this slide illustrates, interestingly, it illustrates on our y-axis the density of our particle starting at low density, okay, smaller numbers at the top, and then finally high density, right? So larger numbers, kind of inverse y-axis here. But high density at the bottom, moving up to low density, and plotting these against the diameter of the particle, okay? What we're looking at, what we started looking at today in exogenous transport would be these VLDLs, which essentially rival the chylomicron in terms of size. What you were seeing and what we just talked about, okay, in terms of the endogenous transport, we're seeing these just reduced right down to this IDL, and then from the IDL down into these LDLs. Okay, and these things just keep shrinking in size as they go along. Okay, and that kind of gives you some concept of what's happening. Okay, the LDLs and the IDLs are derived from the VLDLs. Okay, I think it's important, and this is somewhat illustrated here. It's important to recognize something about this. The HDLs, okay, are not derived from VLDLs. They are separately made in the liver, and we'll talk about reverse cholesterol transport on Wednesday. They are certainly smaller in size than our LDLs, and certainly the VLDLs, but they are not in this progression from the LDLs down, okay? So don't mistake that thinking, oh, well, HDLs are the next step in this process. That's not true. Okay. The protein content in the HDL is very different, and they start off actually small and get larger, okay, as we'll see. Okay. So that gives you some, at least, visual of what might be happening. Of course, the shrinkage in size is because the triglycerides are being removed, primarily triglycerides are being removed from the LDLs. Now, what we will also find out is that cholesterol is being removed as well, okay, the cholesterol esters. And the HDLs play an important role in removing cholesterol from the LDLs. Okay, so we'll talk about that probably on Wednesday. Okay, right. Now, questions on that slide? Yeah. That's correct. Yeah. So if you go to the composition, so the question, if you didn't hear it, it's the proteins are not really changing as you go from VLDLs to IDLs to LDLs. Rather, they just become a greater percent of the weight because you're removing the triglycerides, and that's correct, mostly correct, right? So when we get to here, let's think about now we're at LDLs, okay, and we'll talk about first of all the composition of these. We have seen a fairly significant reduction in the triglycerides going from VLDLs to LDLs. Only about 10% of the weight or the mass of this particle is now triglycerides, okay. Protein, okay, content has gone up in terms of percent mass, primarily though because we're looking at a percent mass. Okay, you are gaining to some extent protein, but for the most part, protein composition is the same. Okay, I say that you are gaining it because there can be transfer of these proteins between particles. So the protein content can change to some extent, okay, but primarily we're looking at a reduction in lipid mass. Yeah. Okay. So LDL composition, right? I mean, you can go across the board here. More protein, obviously, less triglycerides. These are by far, okay, the most enriched in cholesterol esters. Cholesterol esters being, again, very hydrophobic. Okay, what we see down here, and I think this is a decent representation of a VLDL, or of an LDL. Okay, so that's an LDL. Okay. That big greenish blob, this guy here, that kind of encircles the whole protein. I'm sorry, not the whole protein, but the whole particle. That is B100. Okay. The other proteins are there. They're not demonstrated here in this figure, but the other proteins that I mentioned, C2 would be there, and then also ApoE plus others. Okay, so protein composition really hasn't changed all that much. There can change a little bit. Certainly B100 is not going to leave. Okay, so B100 will remain in the LDL particle or part of the LDL particle until the particle's removed from the bloodstream. Okay. Now, the LDLs will then be absorbed, and this is where we're going to see the end of the endogenous pathway. They're going to be absorbed by tissues, so I'll put tissues first, because this can happen in lots of different tissue types. But happens in the liver as well. Okay. Tissues would be, adipose tissue, adrenal glands would be two that I would mention that are pretty important in this. It's not an exhaustive list. The liver, though, is going to be one of the primary organs that uptakes LDLs out of the bloodstream. Okay. You might wonder why I put adrenal glands. They're pretty small, obviously, adrenal glands are, but adrenal glands need a lot of cholesterol because adrenal glands have to produce steroid hormones. Okay, so they will absorb quite a bit of this LDL, take that cholesterol, produce steroid hormones from them, and then release those. Okay. Now the absorption process, so this is going to lead to some interesting topics here. So let's talk about the absorption here. So on this slide, we're looking at absorption. Okay, so this is figure 2141 from the book that I suggested you use in this class. This could be any cell. We'll say it's a liver cell, but it could be really any cell that has the ability to uptake LDL particles. And it's just showing, again, not in a ton of detail, but it's showing the endocytosis of the LDL particle. The big thing here is going to be these LDL receptors, okay? If a tissue is equipped with LDL receptors, then it will bind to and interact with B100, okay? Which is not, I don't think, it is explicitly stated here. So LDL receptor binds ApoB100 on LDL, initiating endocytosis. Endocytosis is a fairly complex process, so there will be lots of factors that would be recruited to the membrane to endocytose the lipoprotein particle. Okay. Now, this then will progress into the cell, okay, as an endosome, and that endosome will actually pinch off, interestingly, and recycle the LDL receptors. There's a limited number of times that LDL receptors can be recycled, okay, and you're consistently losing some as you move through this process. I don't know the exact number. I think that, again, this would be an average. I think that the number, about 100 times they'll be recycled. That sticks out to me. I'm not sure. I haven't read that in a while. But there is a limited number of times that these can be recycled back to the plasma membrane. Okay. How are they marked for destruction? How would the cell know to get rid of those? Topic for another class probably. But they are recycled. Okay. After that, though, as those are removed, these endosomes with the LDL in them, right, so that's LDL in there, will fuse with a lysosome, and the lysosome will just destroy everything, okay, regardless of what cell you're talking about. Okay, the lysosome is going to take that protein, B100 in particular, which is a large protein, they're going to make amino acids out of it. Free fatty acids are going to come out of course, any triglycerides that are left. Cholesterol esters will be converted to cholesterol and free fatty acids. And then finally that cholesterol will be released. Now the cholesterol will be used for like membranes. Okay. It can be used for the production of more cholesterol esters. It can be used for bile salts if this is the liver, or bile acids. Okay. Those are common means of that, or hormones. Okay. Fatty acids can be used for energy or storage. Okay. Amino acids, of course, can be used for energy, okay, or protein production. If this is a liver cell, we would say, okay, endogenous pathway is over. Done. Okay. At that point in time. We'll get to the other half of this slide here in a little bit, in that figure here in a little bit. Okay. Questions on this? One thing I will mention, I'm going to put this in a different color because this is going to come up. Another thing that can be made from cholesterol are oxysterols. Oxysterols describes a pretty large family of cholesterol-containing molecules where a hydroxyl group has been added somewhere along the line in the cholesterol molecule. Okay, it can be in some ways you can think of it as almost a byproduct of cholesterol metabolism. Okay, oxysterols. They are going to play a very important role in our discussion. Okay. All right. Now, let me go ahead and ask you a question, just so we can kind of close this topic out. That's not the question. This is the question, which you can't see. There we go. Okay. So, interestingly, VLDLs rarely undergo endocytosis. Okay, despite the fact that their composition doesn't differ all that much, and in particular the B100 protein is there from the VLDLs, right? So IDLs can undergo endocytosis, but not nearly as often as LDLs. Why do you think that's the case? So think to your neighbor about that. What would be the reason for that? I will Give you a minute 43 seconds to discuss that. On your marks, get set, go. What do you think? Why might that be the case? Okay. Talk about that, and the avalanche, and the Rockies. Okay, about 30 seconds left, so text me an answer if you haven't done so, or start to text me that answer and get something recorded. This will be certainly our only question for today. So you want to get it recorded. What's that?
You want to see Avengers Endgame?
Oh yeah, I gotta get. Well, not this week. I'm not gonna see it, but anyway. All right, 3 seconds. Sometime. Okay, let's check this out. All right, show results. See what people are saying here. Size of the particle. It's too big. Size, I don't know. Magic. There it is. I was hoping someone would get it. Magic. Okay. Due to the size, too big. There. So this. What? I don't know. Like It depends on the inflection of your voice, right? Yeah. Or something like that. I'm not. Something. I'm not entirely sure. Okay, so I think lots of people are hitting on this. In terms of size. It really can be answered just with one word, and that would be size. So, coming back to this slide here, right? The VLDL is beefy, right? Is big, and when you think about this, that B100 protein, there has to be, right, you talked about in 401, you talked about protein-protein interactions and the importance of those in the physiology of the cell and all sorts of things. So for two proteins, though, to interact, they have to have their interfaces exposed to one another. Okay, so what has been demonstrated in these VLDLs is that the interaction phase, or the interface that would interact with the B100, that would interact with the LDL receptor on the B100 protein is actually not exposed in the VLDLs. So those simply don't get absorbed. Not until they really start to shrink in size is enough of the B100 protein revealed that it could then interact with LDL receptors, okay? Which is good. This is a good thing because that means that those free fatty acids and triglycerides can be removed from the VLDLs prior to endocytosis, okay? So that would be why. It's a pretty simple answer, I think. Now, having said all that, and having then covered the endogenous transport, I want to go ahead and start. I don't know if we'll get through this, but I want to go ahead and start on a special topic that's related to the absorption of LDLs out of the bloodstream. So LDLs are commonly referred to as, and you may have heard this, and you may have been even thinking this as we were talking about this, is quote, unquote, bad cholesterol. Right? This is how we will communicate this with the public, that LDL is bad. Okay, and that's true from a cardiovascular standpoint. Okay, any physician will tell you that they would want, okay, your LDL concentration in the blood to be less than 200 milligrams per deciliter. Okay, that's what they want. Okay, we'll talk about HDLs later on. LDL HDL ratios are important too in that health discussion. Okay, but that's what you'd want. That typically will put you at much less risk for cardiovascular events and cardiovascular disease. This would include heart attacks and stroke, right? So those are the two main concerns. Of course, heart attacks and stroke are pretty serious conditions. Okay, as the saying goes, serious as a heart attack. Okay, so you want that LDL bad cholesterol to be in less than 200 milligrams per deciliter. Okay. Now, there are a number of reasons why concentration of LDLs will go up in a person's bloodstream. Diet, not the least of which, is an important factor of that. But I want to go ahead and talk about a fairly extreme example of this in a condition, a genetic condition called familial, okay, and this word is really not easy for me to say, hypercholesterolemia. I got it right. Okay, I kind of rolled off that time. It's a word that is difficult for me to say for some reason. I get to hypercholesterol and then anemia becomes really hard. Okay, so familial hypercholesterolemia. Okay, or I'm just gonna resort to FH. FH is so much easier. Okay, and it's consistent with the literature too. So familial hypercholesterolemia, or FH, is an autosomal dominant genetic disorder. Okay, and individuals that are heterozygous for this okay, they typically will have circulating LDL concentrations that are greater than 300 milligrams per deciliter. So 100 units larger than what would be advisable from a health standpoint. That would be the heterozygous. Homozygous is really serious. So homozygous, these individuals will have LDL concentrations, circulating LDL concentrations greater than 600 milligrams per deciliter. Now, those individuals, homozygous, okay, to give you some sense of how serious this condition is, those individuals can experience cardiovascular disease and events in their teens. Okay, so dying of heart attacks and stroke in the teenage years. Obviously, very, very serious condition. Okay, treatment of the homozygous individual, a lot of times the treatment will resort to a liver transplant, okay, which is an extreme, obviously, medical procedure. There will be complicating factors for the rest of their life, but it can extend their life by transplanting the liver. So that's a very, very serious condition. The heterozygous is also very serious. Those individuals, while they'll make it through their teens, will typically have higher than normal cholesterol for their whole life, and that can cause problems in their early 40s, okay, or even late 30s, depending on how quickly they caught it, what actions they took to prevent cardiovascular disease from forming, including a cocktail of drugs as well as lifestyle changes. Okay. So very serious. Now, why do we bring that up? Well, the reason that we bring that up is because of this. All right. Generally speaking, familial hypocholesterolemia, there it is, FH. Okay. FH, the reason that we bring that up is typically, okay, and there are a number of descriptions of this disease, but are typically mutations in the LDL receptor. Okay. So mutations. And those mutations then prevent the absorption of LDL particles from the bloodstream from tissues, because the gene, this would be, of course, a germline gene, like an inheritable disease. All tissues would be affected by this. Okay. Now, heterozygous, you would have about half of the LDL receptors being produced that were functional. Okay, so that's why the disease is not nearly as extreme, because LDLs are still being removed from the bloodstream by different tissues. Homozygous, both copies of the gene are defective. There is very little, if any, endocytosis of LDLs, and that leads to very serious conditions very early on. Again, liver transplant in that case, what that would do, of course, you would want a liver that comes from someone that doesn't exhibit the FH mutations. That would allow at least one organ to start to absorb significant amounts of LDL from the bloodstream. Okay. So not a funny disease, certainly an interesting disease from a scientific standpoint, for sure. And you can obviously see the relationship to what we're talking about here. Now, some of these, and we'll get to this, I don't know if we'll get to this today, but I will go ahead and mention this. Some of the disease conditions can also be a result in a defection in terms of the production process of the LDL receptor. Okay, so what you're looking at here, and what I just circled, would be, of course, there's the gene in the nucleus that's made, targeted for a rough ER, made in the ER, transported to the Golgi. Golgi then takes it to the plasma membrane and puts the LDL receptors on the plasma membrane. Lots of steps in there, lots of potential problems with that pathway that can result in FH as well. So FH, while we describe it as the one condition, can be the result of several different genetic disorders in an individual. All of them, though, are autosomal dominant, okay, and lead to obviously fairly serious condition. Now, real quickly, let's do this for the last 5 minutes of today. Let's think a little bit about then why is LDL bad cholesterol? What does it do that can cause cardiovascular disease? And what is the pathology of this? So this slide illustrates, again, in a fairly simple way, the pathology of LDL and accumulation of LDL. So let me go ahead and zoom in here. What you're looking at here is a blood vessel. Okay, we have the endothelial cells. So these would be endothelial cells lining that blood vessel or the artery. Okay, and this is kind of deceptive what they're showing here. Okay, but this little box would be here. Okay, essentially the extracellular matrix of the endothelial cells on the outside of the blood vessel. Okay, and what you are looking at here, to give you some concept, these little yellow guys here, and they're even pointing to them, these are LDL. Okay, LDLs have the capacity to certainly slip in between the endothelial cells and get into that extracellular matrix behind the blood vessel. Okay, and they can accumulate there. Obviously, the more LDL you have in the bloodstream, the more, or the higher the propensity of those LDLs to get into that environment and just kind of hang out. Okay, now that can cause problems because those can undergo oxidation, okay, and become what are called OX-LDLs, oxidative stress. Okay, oxidative stress is bad, as we've already mentioned. Okay, and it can happen even in an extracellular environment. How that happens, there's a variety of ways that those can undergo oxidation. Okay, so we'll just say that they can, if they accumulate there, they can and will go undergo oxidation, and that's going to be then a signal to the immune system. So there's going to be an immune response to this. Monocytes, and I'm not an immunologist, so this is all stuff that I won't be able to answer a lot of questions on. All right, but a monocyte can slip in between these endothelial cells. It will be converted to a macrophage, and then the macrophage can actually start to uptake endocytosed LDLs. Okay. The problem with the macrophage is it doesn't really have a capacity to regulate how much LDL is going to take up. So if there's a high concentration of LDL there, it's just going to keep taking it and taking it and taking it. Okay, and what will happen to that cell is it will become what's called a foam cell. All right, and that foam cell gets its name because when you look at these in a microscope, they look kind of milky white. Okay, they're a very unhealthy cell. They will undergo what would be considered apoptosis or necrosis. They'll split open. Necrosis is the worst, so they just dump their contents into the extracellular environment. A lot of that content is hydrophobic, cholesterol rich, because there's a ton of LDL in there that they've taken in through lysosomes. They broke it down into cholesterol or cholesterol esters, and now it just dumps into that extracellular matrix. That will form these plaques. Okay, and that's what you're looking at here. And these plaques are not microscopic, they're macroscopic. That will then, of course, lead to closing of blood vessels. Closing of blood vessels, right, prevents blood supply to get into tissues. If that's in the heart or in the brain, that can lead to a heart attack or a stroke. Okay. The other aspect of this, of course, would be that some of that plaque can actually be broken off in larger blood vessels. Okay. And then you'll have these particles floating through the bloodstream that can then block blood from getting into the heart or the brain. Okay. Some of you are like, you should go, all right? It's yucky, okay? It's not good, all right? So, but that, of course, happens at a much greater extent to the person that has FH, okay? All right, so we'll come back. We'll talk a little bit about treatment of this, besides removing a liver, and talk a little bit about drugs that can be used to help this, okay? All right. Have a good rest of your day.